Welcome, everyone. Have you ever wondered just how many galaxies are out there in the vast expanse of the universe? When scientists first started measuring the number of galaxies, the estimates were in the hundreds of billions. But new discoveries have completely upended these numbers. Thanks to advances in technology, including the work of powerful telescopes like the James Webb Space Telescope, we now know that there are far more galaxies than we initially thought, at least 2 trillion. This revelation gives us a glimpse into just how massive the observable universe really is. To put this into perspective, let's consider the famous Hubble Space Telescope's ultra-deep field image. When astronomers first looked at this small patch of sky, they were able to detect thousands of galaxies, each filled with billions of stars. What's even more mind-blowing is that this was just one tiny sliver of the vast universe. With the help of the Webb Space Telescope, we've been able to peer even deeper into space, seeing galaxies that were once too faint or too distant to observe. The result is a truly mind-boggling realization. The universe is far larger and more diverse than we ever imagined. We used to think that the number of galaxies in the universe was finite, but as our tools have improved, so has our understanding of just how much there is to explore. Galaxies are not just scattered randomly. They are organized in clusters, bound by gravity, forming massive structures. The sheer scale of these formations is hard to comprehend, with galaxies constantly moving and interacting with one another. This process of discovery is ongoing, and each new observation opens up new questions about the origins and future of these cosmic systems. Even more surprising is the scale of the stars that populate these galaxies. The observable universe contains an estimated 200 sextillion stars, a number so large it's nearly impossible to fathom. If we were to attempt to count them, it would take more than a lifetime or even many lifetimes to even scratch the surface. In comparison, the amount of sand grains on all the beaches of Earth seems small. This vast number of stars is what fills the universe with its brilliance and provides the raw material for the formation of planets, galaxies, and life itself. As we dive deeper into understanding the structure of our own local universe, one of the most fascinating discoveries is the organization of galaxies into what we call groups. Our Milky Way galaxy is part of a larger collection of galaxies known as the local group. This group includes several other notable galaxies like Andromeda, the Triangulum galaxy, and a number of smaller galaxies. These galaxies are all bound together by gravity, and they move as a single unit through space. In fact, the Milky Way and Andromeda are on a collision course, with the two galaxies expected to merge in about 4 billion years. While this might sound like a catastrophic event, it's not necessarily the end of life as we know it. Galaxies collide and merge all the time in the universe, and when this happens, new stars are often born in the process. The interaction between these galaxies will result in a massive restructuring of both galaxies, but it won't wipe out everything within them. The stars and planets that exist in these galaxies will most likely continue to orbit in a new configuration, giving rise to an entirely different galactic structure. But this isn't the only type of galactic interaction we observe. In fact, the universe is full of what scientists call galactic cannibalism. This is the process in which a large galaxy pulls in and absorbs smaller galaxies, merging them into one. Our Milky Way is actually in the process of consuming several smaller galaxies, such as the Sagittarius Dwarf Elliptical Galaxy. Over time, the gravitational forces exerted by the Milky Way have stripped these smaller galaxies of their stars, gas, and dust, pulling them into the larger galaxy and integrating them into the Milky Way's overall structure. This process of galactic cannibalism is a common feature of the universe, with larger galaxies growing by consuming their smaller neighbors. In the case of the Milky Way, these mergers may have contributed to its current size and structure, and they may even continue in the future as more galaxies are absorbed. Looking beyond our local group of galaxies, we find even more complex structures like superclusters. These massive groupings of galaxies are bound together by gravity and can span vast distances. The supercluster we belong to is called Laniakea, and it contains thousands of galaxies, including the Milky Way. This supercluster, along with others like it, forms part of a massive cosmic web that stretches across the universe. The Laniakea supercluster is not just a collection of galaxies, but a massive interconnected structure that shapes the flow of galaxies across the universe. Gravitational forces pull galaxies toward these superclusters, creating a cosmic network that is far more organized than we once thought. At the center of the Laniakea supercluster, and other superclusters, there exists a gravitational anomaly known as the Great Attractor. This is a mysterious and massive concentration of mass that exerts a pull on galaxies across vast distances, including our own. The exact nature of the Great Attractor is still not fully understood, but it plays a crucial role in the movement of galaxies across the universe. The discovery of the Great Attractor is one of the key pieces of evidence that supports the idea of a large-scale structure in the universe that affects the motion of galaxies on a cosmic scale. As our telescopes and instruments improve, we are learning more about these structures and the way they influence the universe as a whole. As we continue to explore the structure of the universe, we must consider the dynamic forces at work within galaxy clusters. These clusters, which are groups of galaxies held together by gravity, are some of the most fascinating and energetic environments in the cosmos. They are the sites of constant activity, where galaxies move at incredible speeds, often crashing into each other and merging in the process. This phenomenon, known as galactic harassment, occurs when galaxies in close proximity to each other interact gravitationally, causing them to lose their gas and distort in shape. Over time, these interactions can lead to the destruction of smaller galaxies, which are absorbed into larger ones, further contributing to the growth and evolution of these massive structures. One of the most well-known examples of this is the Coma cluster, a dense galaxy cluster located about 320 million light-years from Earth. Within this cluster, galaxies are constantly colliding and merging, and the intense gravitational forces involved can strip away the gas and stars from these galaxies. This process plays a crucial role in the evolution of galaxy clusters, as it helps to shape the distribution of galaxies within them and contributes to the ongoing formation of new stars. The gravitational interactions that occur in these clusters also provide insights into the mysterious substance known as dark matter. Dark matter is a form of matter that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. However, scientists have been able to infer its existence by observing the effects it has on visible matter. One of the key ways we study dark matter is by looking at how it bends light through a process called gravitational lensing. When light from a distant galaxy passes through a galaxy cluster, the mass of the cluster bends and distorts the light, creating a lens effect that can be used to map the distribution of dark matter. This phenomenon has been observed in several galaxy clusters, providing us with valuable information about the presence and distribution of dark matter. In fact, some of the most detailed maps of dark matter have come from studying the gravitational lensing effects in galaxy clusters. These observations suggest that dark matter makes up a significant portion of the total mass in the universe, and it plays a crucial role in the formation and evolution of large-scale cosmic structures. Interestingly, the discovery of dark matter has led to the identification of another fascinating phenomenon: dark galaxies. These are galaxies that contain large amounts of mass, but emit little to no visible light. They are difficult to detect because they do not radiate in the same way that normal galaxies do, but scientists have been able to find them by observing their gravitational effects on surrounding matter. Dark galaxies are thought to contain vast amounts of dark matter, and their discovery has opened up a new area of research in cosmology. These dark galaxies are intriguing because they challenge our traditional understanding of how galaxies form. If dark matter is indeed a key component of these galaxies, then it raises the question of whether dark matter plays a more fundamental role in galaxy formation than we have previously realized. The study of dark galaxies may one day provide answers to some of the biggest questions in cosmology, such as the true nature of dark matter and how galaxies evolve over time. As we zoom out and look at the largest structures in the universe, we encounter the cosmic web, a vast network of galaxies and dark matter that spans the entire observable universe. This web-like structure is made up of galaxies that are connected by huge filaments of dark matter, forming a complex and interconnected framework that defines the large-scale structure of the cosmos. These filaments, known as cosmic voids, are vast regions of space that contain few or no galaxies, and they are surrounded by these massive filaments of galaxies, forming the skeleton of the universe. The cosmic web is not just a random arrangement of galaxies. It is a product of gravitational forces that have shaped the universe over billions of years. In fact, scientists believe that the cosmic web was formed through the slow accumulation of matter in the early universe. The gravity of dark matter and galaxies gradually pulled everything together, creating these giant structures. The process of galaxy formation and clustering began shortly after the Big Bang, and over time, the universe evolved into the highly organized structure we see today. One of the largest and most well-known structures in the cosmic web is the Laniakea supercluster, which includes our own Milky Way galaxy. This supercluster is one of the largest known structures in the universe, spanning over 500 million light-years and containing thousands of galaxies. The Laniakea supercluster is just one of many superclusters that make up the cosmic web, and its sheer size and scale give us a sense of how vast and interconnected the universe really is. But the cosmic web is not static. It is constantly evolving and changing as galaxies move through space and interact with one another. Over time, the gravitational pull between galaxies and superclusters will continue to shape the web, causing galaxies to collide, merge, and form new structures. This process is ongoing, and as we look deeper into space, we are seeing the universe in a constant state of flux, with new galaxies and structures being formed all the time. This dynamic nature of the cosmic web has led scientists to propose that the universe itself is a living, evolving system, much like an organism. Just as cells in a body work together to maintain the overall function of the organism, galaxies in the cosmic web are interconnected and work together to shape the larger structure of the universe. This idea suggests that the universe is not just a collection of isolated objects, but a highly organized and interconnected system that is constantly adapting and evolving. As we continue to study the cosmic web, we are learning more about how galaxies form and evolve over time. The discovery of the large-scale structure of the universe has provided new insights into the origins of galaxies and the forces that shape them. We are also learning more about the mysterious role of dark matter, which provides the framework for these massive structures and helps to hold the cosmic web together. One of the most fascinating aspects of the universe is its largest structures, often referred to as Great Walls. These massive, almost unimaginable formations are colossal concentrations of galaxies, stretching across hundreds of millions of light-years. The Sloan Great Wall, discovered in 2003, is one of the most famous examples of such a structure. This Great Wall consists of over 80,000 galaxies, and it spans more than 1.3 billion light-years across. To put that into perspective, the entire Milky Way galaxy, including its spiral arms, is only about 100,000 light-years in diameter. The Sloan Great Wall is a prime example of how the universe is not just a random scattering of galaxies, but instead exhibits enormous, organized structures. Even more remarkable is the discovery of the Hercules Corona Borealis Great Wall, which is currently considered the largest known structure in the universe. This massive wall of galaxies stretches over 10 billion light-years across, making it more than 100 times larger than the Sloan Great Wall. The sheer scale of these structures challenges our understanding of the universe's formation and the forces that shaped it. Scientists are still working to understand how these enormous structures came to be, and what their existence means for the overall structure of the universe. Great walls like these are not just isolated phenomena. They are part of a larger pattern of galaxy clusters and superclusters that stretch across the universe. These immense structures are interconnected, forming a vast cosmic network that spans the observable universe. The discovery of such large-scale structures has profound implications for our understanding of the universe's evolution It suggests that the distribution of galaxies is not random, but rather follows a complex organized pattern that is influenced by gravity and dark matter. But these great walls are not permanent. Just as galaxies can collide and merge, these massive structures are constantly evolving and changing. Over billions of years, the galaxies within these great walls will interact with one another, exchanging stars, gas, and other cosmic materials. Some galaxies will merge, forming even larger galaxies, while others will be torn apart by the immense gravitational forces at play. The great walls themselves will continue to grow, shrink, and shift over time, reshaping the cosmic landscape. The discovery of these enormous structures has also led to new questions about the nature of the universe. Are they the largest structures that exist, or are there even bigger formations yet to be discovered? And how do these structures fit into the larger framework of the universe? Do they represent the final stage of cosmic evolution, or are they just stepping stones in the ever-expanding story of the universe's development? In addition to these massive galaxy clusters and superclusters, the universe is also filled with vast regions known as cosmic voids. These are enormous expanses of space that contain very few galaxies, and they represent some of the most mysterious and least understood areas in the cosmos. The voids are vast, often spanning hundreds of millions of light years, and they are mostly empty, with very little visible matter. These voids are not completely devoid of everything, however. Some galaxies can still be found within them, but the density of galaxies is much lower compared to the surrounding structures. The existence of these cosmic voids is critical to understanding the large-scale structure of the universe. They are the gaps in the cosmic web, where the filaments of galaxies and dark matter stretch out and form vast expanses of emptiness. What's fascinating is that these voids are not simply random. They are the result of the gravitational forces that shape the universe, and they provide valuable clues about the way galaxies and clusters form over time. Voids are created when the gravitational pull of nearby structures causes matter to accumulate into filaments, leaving behind large regions of empty space. Cosmic voids also play a crucial role in the expansion of the universe. As the universe continues to expand, the voids grow larger, and the galaxies within them drift further apart. This expansion is driven by the mysterious force known as dark energy, which is responsible for the accelerating rate at which the universe is stretching. As the galaxies within these voids move away from each other, the voids themselves continue to expand, and the space between galaxies grows. This expansion is a fundamental aspect of the universe's evolution, and it offers key insights into the forces that govern the cosmos. Even though voids are empty of visible matter, they are not devoid of influence. Recent studies have shown that voids can affect the surrounding galaxies in subtle ways. For example, galaxies that lie on the edge of voids often experience a slight tug or distortion in their motion due to the absence of mass in the void itself. This effect is called the cosmic void effect, and it highlights how the structure of the universe is shaped not just by the presence of matter, but also by the absence of it. Voids, in essence, are not just empty spaces but active regions that influence the motion and evolution of galaxies and other cosmic structures. The study of these voids has led scientists to propose new theories about the universe's origins and structure. One intriguing idea is that voids might provide clues about the very early universe, potentially shedding light on the forces that shape the formation of galaxies and large-scale structures. Some researchers even suggest that studying voids could help us understand the nature of dark energy, the mysterious force that is causing the universe to accelerate. As our understanding of voids deepens, it may open up new avenues for exploring the fundamental mysteries of the universe. As our understanding of the universe continues to grow, we're also gaining new insights into the intricate relationship between galaxies, dark matter, and the evolution of cosmic structures. One of the most important discoveries in recent years has been the realization that dark matter isn't just a passive component of the universe, it's an active force that shapes the large-scale structure of the cosmos. Dark matter makes up about 85% of the total mass of the universe, yet it interacts with regular matter in ways that are still not fully understood. It doesn't emit or absorb light, making it nearly impossible to detect directly. However, scientists have been able to study its effects on visible matter, especially through the phenomenon known as gravitational lensing. Gravitational lensing occurs when the gravitational pull of a massive object, like a galaxy or a cluster of galaxies, bends and distorts the light from more distant objects behind it. This effect allows astronomers to map the distribution of dark matter in the universe, even though it's invisible to traditional telescopes. By observing how light is bent around galaxies and galaxy clusters, scientists can infer the location and amount of dark matter present. This has been a key method for understanding how dark matter influences the formation and evolution of galaxies and large-scale structures. One of the most exciting discoveries in this field came from the study of galaxy clusters. These massive collections of galaxies are some of the largest structures in the universe, and they provide an excellent laboratory for studying dark matter. In particular, researchers have used gravitational lensing to map the distribution of dark matter in these clusters, revealing that dark matter is not only present in large quantities, but is also playing a key role in the formation of galaxies. Without dark matter, the galaxies within these clusters wouldn't have enough mass to stay bound together, and they would likely be torn apart by the forces at work in the universe. Another fascinating aspect of dark matter is its role in galaxy formation. According to current models, dark matter provides the gravitational framework around which galaxies form. As matter clumps together under gravity, dark matter helps to pull in normal matter, forming the dense cores of galaxies. These dark matter halos are thought to be the seeds of galaxy formation, and their influence can be seen in the way galaxies are distributed across the universe. Scientists believe that galaxies are not scattered randomly, but rather are organized in a way that follows the gravitational pull of dark matter. Despite these discoveries, dark matter remains one of the biggest mysteries in cosmology. We know it exists because of its gravitational effects on visible matter, but we don't yet understand what it's made of. Some scientists believe that dark matter could be composed of exotic particles, such as weakly interacting massive particles, WIMPs, which would only interact through gravity and the weak nuclear force. Others suggest that dark matter might be made up of even more unusual particles, such as axions or sterile neutrinos, until we can directly detect dark matter. However, these ideas remain speculative, and the true nature of dark matter remains one of the most pressing questions in modern physics. In addition to dark matter, another intriguing aspect of the universe is the discovery of dark galaxies. These mysterious entities contain large amounts of mass but emit little to no light. This makes them incredibly difficult to detect, as traditional telescopes rely on visible light to observe galaxies. However, scientists have managed to spot these dark galaxies by studying their gravitational effects on surrounding objects. Even though dark galaxies don't shine like regular galaxies, they still exert gravitational influence, which allows astronomers to infer their presence. Dark galaxies are thought to be composed mostly of dark matter, with very little visible matter like stars or gas. This makes them vastly different from the galaxies we are familiar with, which contain large amounts of visible matter. The fact that dark galaxies exist challenges our traditional understanding of galaxy formation. We typically think of galaxies as glowing islands of stars, gas, and dust, but dark galaxies defy this norm. They are mostly made of invisible dark matter, with very little visible matter, and yet they still have mass and gravitational influence. The discovery of dark galaxies has raised new questions about the role of dark matter in the formation and evolution of galaxies. Could dark matter be responsible for the formation of entire galaxies that are hidden from view? If dark matter is the key ingredient in galaxy formation, then these dark galaxies could represent a fundamental step in the process of galactic evolution. Scientists are still studying dark galaxies to understand how they formed, why they are so difficult to detect, and what role they play in the broader structure of the universe. One theory is that dark galaxies could be the remnants of older galaxies that have lost their visible matter over time. Perhaps these galaxies once contained stars, gas, and dust, but over billions of years, their visible matter was stripped away or dissipated. This process could have been triggered by interactions with other galaxies or the gravitational forces of larger structures, like galaxy clusters. If this is the case, then dark galaxies could provide valuable insights into the history of the universe and the processes that have shaped the galaxies we see today. Another possibility is that dark galaxies are still in the process of forming. If dark matter plays a central role in galaxy formation, then these dark galaxies could be the early stages of galaxy evolution. As more visible matter accumulates over time, these dark galaxies could eventually begin to glow and form stars, becoming more like the galaxies we are familiar with. This would mean that dark galaxies represent an earlier phase in the life cycle of galaxies, and their discovery could offer a glimpse into the future of galaxy formation. As we continue to explore the universe, one of the most awe-inspiring and perplexing features is the cosmic web. The cosmic web is a vast and complex structure that connects galaxies, clusters, and superclusters in a way that resembles a giant interconnected network. It's not just a random arrangement of galaxies. It's a highly organized structure, shaped by the forces of gravity and dark matter. The cosmic web is made up of long, thread-like filaments of galaxies and dark matter that stretch across the universe, forming the largest known structure in the cosmos. These filaments are interconnected, creating a vast network that defines the large-scale structure of the universe. What's particularly fascinating about the cosmic web is that it's not static. Just as galaxies move and evolve over time, so does the cosmic web itself. The filaments of galaxies and dark matter are constantly shifting, and new structures are continually being formed as gravity pulls matter together. Over billions of years, the cosmic web has grown and evolved, shaping the large-scale structure of the universe into the vast network we observe today. At the heart of the cosmic web lie galaxy clusters and superclusters, which are the largest structures in the universe. These massive clusters are made up of thousands of galaxies that are bound together by gravity. They are the nodes of the cosmic web, and they sit at the intersections of the filaments that connect them. These clusters are home to some of the most energetic phenomena in the universe, including supermassive black holes and galaxy mergers. The gravitational forces at work in these clusters are immense, and they play a crucial role in shaping the distribution of galaxies throughout the universe. One of the most famous superclusters is the Laniakea supercluster, which contains our own Milky Way galaxy. Laniakea is vast, spanning over 500 million light-years and containing thousands of galaxies. It's just one of many superclusters that make up the cosmic web, and together, these superclusters form a giant interconnected structure that stretches across the observable universe. The discovery of the cosmic web has transformed our understanding of the universe's large-scale structure, revealing just how interconnected everything is. But the cosmic web is more than just a network of galaxies. It's also a map of the distribution of dark matter. Dark matter is an invisible substance that makes up about 85% of the mass in the universe. It doesn't emit or interact with light, which makes it invisible to traditional telescopes. However, scientists can infer its presence by observing its gravitational effects on visible matter. The cosmic web itself is made up largely of dark matter, which provides the framework for the galaxies and clusters that make up the universe's large-scale structure. Without dark matter, the cosmic web would not exist in its current form. Dark matter acts as the scaffolding that holds the universe together, influencing the formation of galaxies, clusters, and the cosmic web itself. In addition to the cosmic web, there is another layer to the universe's vast structure: the largest known cosmic structures, superclusters, and the walls that form around them. These superclusters are the most massive known gravitationally bound structures in the universe, and they represent the largest scale on which galaxies are grouped together. While galaxy clusters are groups of hundreds or thousands of galaxies bound by gravity, superclusters are collections of galaxy clusters that span hundreds of millions of light-years. These structures are interconnected by long filaments of dark matter and galaxies, forming the largest structures in the universe. The boundaries of these superclusters are not uniform, and they are often separated by vast expanses of empty space known as voids. One of the most extraordinary examples of this scale is the Sloan Great Wall, which was discovered in 2003. This massive structure, measuring about 1.3 billion light-years across, is made up of thousands of galaxies and forms a colossal wall in the universe. The Sloan Great Wall is one of the largest structures known to humanity, and its sheer size is difficult to comprehend. It is so vast that it challenges our understanding of the universe's large-scale structure. The fact that such a structure exists tells us just how interconnected the universe is on the largest scales and how gravitational forces shape the distribution of galaxies. Even more remarkable is the discovery of the Hercules Corona Borealis Great Wall, which is considered the largest known structure in the universe. This colossal wall spans over 10 billion light-years and is made up of hundreds of thousands of galaxies. It is over 100 times larger than the Sloan Great Wall, and its sheer size dwarfs anything we could have imagined in the past. The Hercules Corona Borealis Great Wall is not just a single cluster of galaxies, it's an immense network of interconnected galaxies that stretches across a significant portion of the observable universe. Its discovery has reshaped our understanding of the largest cosmic structures and shown just how vast and interconnected the universe truly is. These great walls are not just curiosities, they are key to understanding how the universe has evolved. These large structures are the product of billions of years of cosmic evolution, shaped by the forces of gravity and dark matter. They represent the ultimate end result of the process of galaxy formation, and studying them can give us insight into the forces that drive the universe's growth. The discovery of these massive structures is just one example of how much we have yet to learn about the universe. As our telescopes and observational techniques improve, we will undoubtedly uncover even larger structures and gain a deeper understanding of the cosmos. The discovery of these vast structures has not only expanded our knowledge of the universe but also challenged some of the assumptions we once had about its size and complexity. One of the most intriguing aspects of these great walls and superclusters is the realization that they are not isolated from one another. Instead, they form part of a larger, interconnected network, the cosmic web, where galaxies and dark matter filaments are linked together in a complex, evolving structure. This web-like formation is not just a random collection of galaxies, it is the very blueprint of the universe, shaped by gravitational forces and the distribution of dark matter. One of the most profound implications of these discoveries is the realization that the universe is not just an empty void, but a highly structured and organized system. Far from being an isolated or chaotic expanse, the universe is governed by a set of fundamental rules that dictate the formation and movement of galaxies, clusters, and superclusters. The cosmic web is a reflection of these underlying principles, revealing the large-scale structure of the cosmos. It is a dynamic, constantly evolving network, where galaxies are pulled together by gravity, interacting, colliding, and merging over time. Another fascinating aspect of the cosmic web is its role in the expansion of the universe. As the universe continues to expand, galaxies are moving further apart, with some parts of the cosmic web stretching faster than others. This expansion is driven by the mysterious force of dark energy, which is causing the universe to accelerate at an ever-increasing rate. As dark energy continues to dominate the expansion of the cosmos, it is slowly pulling galaxies farther and farther apart. The influence of dark energy on the cosmic web is still not fully understood, but its impact on the large-scale structure of the universe is undeniable. The study of the cosmic web and the forces that shape it is still in its early stages, but it has already provided us with invaluable insights into the nature of the universe. As astronomers and physicists continue to probe deeper into the mysteries of the cosmos, they are uncovering new details about how galaxies form, how dark matter influences their growth, and how the universe's large-scale structure has evolved over billions of years. The cosmic web is a key piece of the puzzle, and understanding it will be crucial to understanding the universe as a whole. While we continue to explore these vast cosmic structures, One of the most striking discoveries is the role of voids in the universe. These vast regions of emptiness, which contain very few galaxies, are just as crucial to understanding the universe's structure as the dense clusters of galaxies and superclusters. Cosmic voids, as they are called, are not simply empty spaces. They are a key feature of the cosmic web. They represent areas where the gravitational forces from surrounding galaxies and dark matter are weaker, allowing these regions to remain largely devoid of matter. Interestingly, voids aren't just passive empty spaces. They are dynamic and constantly evolving. Over time, these voids expand, pushing galaxies away from each other as the universe continues to expand. The study of cosmic voids provides valuable insights into the large-scale structure of the universe and the forces that shape it. These regions of space are the result of the gravitational interactions that occur between galaxies and dark matter. As galaxies are pulled together by gravity, they tend to cluster in filaments, leaving behind vast stretches of empty space. Voids are the largest known structures in the universe, and they occupy about 80% of the observable universe. Despite being so empty, voids are far from inert. They can influence the movement and evolution of galaxies. For example, galaxies on the edge of voids often move more slowly than those in more dense regions of the universe. This is because the gravitational pull in voids is weaker, causing galaxies to experience less resistance as they move through space. In addition, the edges of voids can sometimes act as gravitational attractors, pulling galaxies toward them. This can create complex, unpredictable patterns in the movement of galaxies, further emphasizing the interconnected nature of the cosmic web. Voids also have an interesting relationship with dark energy, the mysterious force responsible for the accelerating expansion of the universe. Dark energy is thought to be more prevalent in voids, which could explain why these regions are expanding so rapidly. The greater influence of dark energy in voids could be one of the reasons why they continue to grow larger over time. This relationship between dark energy and voids is still an area of active research, as scientists work to better understand the nature of dark energy and its role in the universe's expansion. One of the most fascinating phenomena related to voids and galaxy clusters is the impact that these large-scale structures have on the movement of galaxies across the universe. The influence of gravity is not just restricted to galaxies within clusters or superclusters. It extends over vast distances, affecting the motion of galaxies in areas far beyond these dense regions. This interconnectedness of galaxies, dark matter, and gravitational forces is one of the key features of the cosmic web. As galaxies move through the universe, they are not just drifting aimlessly. They are being pulled and influenced by the gravitational forces of the structures they are part of. In fact, galaxies are not moving randomly. They are following the paths laid out by the large-scale structures of the cosmic web. Just as streams of water flow along the path of least resistance, galaxies follow the filaments of dark matter and the gravity wells of galaxy clusters. These paths are not always straight, and galaxies often experience changes in their motion as they are drawn into new regions of the cosmic web. This movement of galaxies is also influenced by the expansion of the universe. As space itself expands, galaxies are carried along, with those in the more distant parts of the universe receding from us at faster rates due to the expansion. However, this expansion is not uniform. In regions like galaxy clusters, gravity can counteract the effects of cosmic expansion, causing galaxies to move toward each other, while in voids, galaxies tend to move more freely, away from the dense areas. In the past few decades, astronomers have discovered that this cosmic movement is not only influenced by gravity, but also by the mysterious force known as dark energy. Dark energy is the force responsible for the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing rate. The more we learn about dark energy, the more we realize just how significant its influence is on the large-scale structure of the universe. The effects of dark energy can be seen in the way galaxies in voids move apart, while galaxies in denser regions are held together by gravity. But what's particularly interesting is that dark energy is not evenly distributed across the universe. Its influence is felt most strongly in the empty spaces between galaxy clusters, where there is less matter to counteract its pull. As a result, voids are expanding faster than the regions around them, pushing galaxies away from each other and further expanding the cosmic web. This discovery has led to a deeper understanding of how the universe is evolving and how its large-scale structure is shaped by both gravity and dark energy. As we push the boundaries of our understanding of the universe, one of the most exciting areas of research involves the study of the largest structures in the cosmos, the cosmic voids. These vast expanses of space, which contain very few galaxies, are still some of the most mysterious and least understood regions in the universe. They account for roughly 80% of the observable universe, making them one of the most significant features in the large-scale structure of the cosmos. Despite being relatively empty in terms of visible matter, cosmic voids play an important role in the universe's evolution. The absence of galaxies in these areas means that the cosmic web is less dense in these regions, allowing dark matter and gravitational forces to influence the surrounding structures. In fact, voids are created by the accumulation of matter in the cosmic web, as gravity pulls galaxies and dark matter into filaments, leaving vast gaps in between. The expansion of the universe also contributes to the growing size of these voids, as galaxies move farther apart over time. What's fascinating about voids is that they aren't completely empty. While they contain fewer galaxies, voids are still filled with dark matter, gas, and other forms of unseen matter. These regions, despite their lack of visible galaxies, are not entirely devoid of influence. Dark energy, the mysterious force responsible for the accelerating expansion of the universe, is thought to be more prevalent in voids, further contributing to their growth over time. As the universe continues to expand, voids will continue to grow, further stretching the fabric of space. One of the most surprising aspects of voids is their effect on galaxy motion. Even though voids are empty of visible matter, galaxies located near the edges of these voids can still feel the gravitational pull of the surrounding structures. These galaxies move more slowly than those in denser regions of the universe, as the gravitational influence in voids is weaker. Additionally, the edges of voids can act as gravitational attractors, pulling galaxies toward them and causing their motion to become more complex and unpredictable. This movement further emphasizes the interconnected nature of the universe's large-scale structure. The study of voids has revealed new insights into the evolution of the universe. For instance, voids are thought to have played a role in the formation of galaxies. In the early universe, regions with lower densities of matter, like voids, were less affected by the forces that shaped larger structures, allowing galaxies to form independently. Over time, as the universe expanded and matter became more concentrated, galaxies began to cluster together, leaving behind the voids we observe today. In addition to the vast voids and galaxies that make up the cosmic web, there's another feature of the universe that stands out: its ever-expanding nature. The universe's expansion isn't uniform. It's not just a steady increase in distance between galaxies. Instead, galaxies in different regions experience varying rates of expansion due to the gravitational influence of large-scale structures and dark energy. This expansion is a result of the universe's initial conditions following the Big Bang, where space itself began to stretch, carrying galaxies with it. The rate at which this expansion occurs has been accelerating over the past few billion years, primarily due to the mysterious force known as dark energy. Dark energy is still not fully understood, but it is thought to make up about 68% of the total energy content of the universe. Its role is to push galaxies apart, counteracting the attractive force of gravity. As dark energy continues to dominate, galaxies are being pulled away from each other at an ever-increasing rate. This has far-reaching consequences for the future of the universe. In a few billion years, galaxies that are currently within reach of our telescopes will be so far away that they will no longer be observable. The universe will continue expanding, but more and more distant regions will become unreachable, leaving us with only a view of the local group of galaxies. The discovery of dark energy has fundamentally changed our understanding of the cosmos. Initially, scientists believed that the expansion of the universe would slow down over time due to gravity's pull. However, the opposite is happening. The expansion is speeding up. This surprising revelation has led to the conclusion that dark energy must be driving this acceleration. Understanding dark energy is one of the most pressing questions in cosmology today, as it holds the key to unlocking the fate of the universe. Will dark energy eventually cause galaxies to drift apart so much that the universe becomes a cold, dark, and isolated place? Or is there something more to dark energy that we have yet to discover? In the coming years, scientists will continue to explore dark energy through various means. One important tool for studying this force is the observation of supernovae. These distant explosions, which occur when massive stars die, can serve as standard candles for measuring the distance to galaxies. By observing how the brightness of these supernovae changes over time, astronomers can gain insights into the rate of expansion of the universe. Other methods, such as studying the cosmic microwave background radiation and large-scale galaxy surveys, will also help refine our understanding of dark energy. As we continue to explore the universe and its expansion, one of the most fascinating aspects of this cosmic evolution is the discovery of the largest structures in the universe, known as the Great Walls. These colossal formations are some of the largest known structures in the universe, stretching across billions of light-years and containing vast numbers of galaxies. The most famous of these structures is the Sloan Great Wall, discovered in 2003, which is made up of over 80,000 galaxies spread across 3 billion light-years. To put that in perspective, the Milky Way galaxy, our home galaxy, is only about 100,000 light-years across. The Sloan Great Wall is a massive network of galaxies, organized in a wall-like formation that is truly mind-boggling in scale. Even more impressive than the Sloan Great Wall is the Hercules Corona Borealis Great Wall, which is currently considered the largest known structure in the universe. Spanning more than 10 billion light-years, this enormous structure contains hundreds of thousands of galaxies and stretches far beyond what we ever thought possible. Its discovery has completely changed our understanding of the universe's large-scale structure, as it is far larger than anything we previously imagined. These walls, made up of vast galactic clusters, filaments of dark matter, and other cosmic materials, are interconnected in ways that reveal the complex and highly organized nature of the cosmos. These great walls are not just static structures, they are dynamic and ever-changing, constantly evolving over billions of years. As galaxies within these walls interact with each other, they undergo a series of cosmic processes, such as mergers, collisions, and the formation of new stars. These interactions drive the evolution of galaxies and play a key role in the growth of larger cosmic structures. For example, when galaxies collide within a great wall, they can form new galaxies or trigger bursts of star formation, contributing to the overall structure of the wall. This process of galaxy mergers and star formation is a fundamental part of how the universe evolves. Despite their enormous size, great walls are not the only large-scale structures in the universe. Superclusters, like the Laniakea supercluster, are also critical to understanding the universe's large-scale structure. Superclusters are massive collections of galaxies, each containing thousands of individual galaxies, and they are the largest gravitationally bound structures in the universe. These superclusters are interconnected through a vast network of dark matter filaments, and they form the building blocks of the cosmic web. The study of these structures has revealed just how interconnected the universe really is, with galaxies and superclusters forming a complex web that stretches across the observable universe. As we continue to map the universe and discover more about its vast structure, one of the most important factors influencing its formation is the presence of dark matter. Dark matter, which makes up about 85% of the total mass of the universe, does not emit, absorb, or reflect light, making it invisible to traditional telescopes. Yet, despite its elusive nature, dark matter plays a crucial role in the formation of galaxies and the large-scale structure of the cosmos. Without dark matter, galaxies would not have enough mass to remain intact, and the universe as we know it would be drastically different. The gravitational effects of dark matter can be observed through a phenomenon known as gravitational lensing. When light from distant galaxies passes near a massive object, such as a galaxy cluster, the object's gravity bends the light, creating a lens effect that distorts the image of the background galaxy. This effect allows scientists to map the distribution of dark matter by studying how it bends the light from distant galaxies. In this way, dark matter can be detected indirectly by observing its gravitational influence on visible matter. One of the most striking examples of dark matter's influence comes from galaxy clusters, where the mass of dark matter is concentrated in large halos surrounding galaxies. These halos are invisible to traditional telescopes, but their gravitational effects can be measured by observing the motion of galaxies within the cluster. Without dark matter, the galaxies within a cluster would be torn apart by the gravitational forces at play, but the presence of dark matter provides the necessary gravitational binding to keep the cluster intact. Even though dark matter has been observed through its gravitational effects, its exact nature remains one of the biggest mysteries in cosmology. Scientists have proposed several candidates for what dark matter might be made of, including weakly interacting massive particles, WIMPs, and axions. These particles are thought to interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Despite years of research and experimentation, dark matter has yet to be directly observed. However, the search for dark matter continues, and new experiments are being developed to detect its presence in a more direct way. Understanding dark matter is crucial, not only for understanding the formation of galaxies and clusters, but also for gaining a deeper insight into the overall structure and fate of the universe. Dark matter's influence extends across vast cosmic distances, shaping the distribution of galaxies and superclusters. As scientists continue to study dark matter, they are also unraveling the mysteries of the universe's largest structures, including the cosmic web and the vast filaments of dark matter that interconnect galaxies across the cosmos. As our understanding of dark matter and cosmic structures deepens, we begin to see how the universe is constantly evolving, and how the forces that shape it are interconnected. The discovery of dark energy, for instance, has added a new layer of complexity to our understanding of the cosmos. Dark energy is the mysterious force driving the accelerated expansion of the universe. Unlike dark matter, which pulls galaxies together, dark energy pushes them apart. It makes up about 68% of the universe's total energy content, yet its exact nature is still unknown. What's truly fascinating about dark energy is how it influences the large-scale structure of the universe. In regions where dark energy's influence is stronger, galaxies are moving away from each other at an accelerated rate, causing voids to grow larger over time. This expansion is not uniform, and it's driven by the energy that permeates all of space, pushing galaxies apart. As the universe continues to expand, dark energy will continue to dominate, reshaping the cosmic web, and possibly even altering the way galaxies interact with each other. The future of the universe, then, is tied to the ongoing interaction between dark matter, dark energy, and gravity. These three forces are the key to understanding the fate of galaxies and the large-scale structure of the cosmos. Will dark energy continue to accelerate the expansion of the universe until galaxies are too far apart to interact? Or will the gravitational pull of dark matter and other cosmic forces eventually slow the expansion, leading to a new cosmic phase? As we continue to explore the universe with powerful tools like the James Webb Space Telescope, we're uncovering new answers to these questions. With each new discovery, we're gaining a deeper understanding of the forces that shape the universe. Whether it's the cosmic web, the evolution of galaxies, or the nature of dark matter and dark energy, we're only beginning to scratch the surface of the universe's vast mysteries. The journey ahead promises to be one of the most exciting in the history of science, as we continue to push the boundaries of knowledge and explore the universe on scales unimaginable just a few decades ago.